Okay, so you can see. Hello everyone, I'm Shoichi Kawamoto from Joint Christian University in Taiwan. This is in the same town as the Taiwan International Airport that probably most of you used some days ago. And today I'm going to talk about some observation in the field theory on the non-commutative space. So let me start with some motivation. So my motivation is quantum gravity, and in quantum gravity, we somehow expect that we need to give up some notion of the smooth geometry at the Planck scale. For example, in the string theory or M theory membranes, for example, we consider some bunch of D-branes and some space-time provide D-branes. The information of the location will be encoded in the matrix elements of the large matrices. So in some sense, then the space-time built by the D-branes will be the part of the matrices and may not be commuting to each other, and it's not really fit to the smooth geometry structure. And of course, at this moment, we don't know the exact definition or exact notion of the quantum geometry yet. So, but there are some hints that some simple types of the quantum geometry, namely the non-commutative geometry, where the coordinates are not really commuting to each other, will be a nice toy model of quantum geometry. So today, I consider some field theory on this type of non-commutative geometry. Today I use a fuzzy sphere, which is a non-commutative version of the smooth sphere. It's a finite linear approximation of the smooth sphere. So this is my model here. So introducing a fuzzy sphere is simple. Just this is the definition of S2, and I just replace this coordinate x to be the some non-commutative operators for some matrices. Okay. In terms of field theory, so I start with some scalar field, scalar 5 to the 4th theory on sphere, and then any field can be expanded with respect to the spherical harmonics. Okay. Then I replace this spherical harmonics with some large matrices that obey the similar algebra field theory, and then this smooth field theory can be replaced with some matrix model, which can be regarded as a field theory on the fuzzy sphere. Roughly speaking, I just introduced this L corresponds to the momentum, so I just introduced some large cutoff 2L for the old quantum field. Then I introduced some quantum field theory on fuzzy sphere. One interesting observation for this model is that, so in this case, this is 4-point lattices, so each field are not commuting to each other, so the order of the field is now important. So if you calculate 2-point function at one loop, then there will be some distinction between planar contraction and non-planar contraction. Okay? So the director of this institute, NCTS, and the collaborators have observed that in non-commutative case, there would be some difference remains. And this kind of the difference can be interpreted as if you take a non-commutative plane limit, this is related to the well-known interesting phenomenon called the UV-IR mixing, which is that some divergence of the one-loop diagram, some UV divergence is related to the IR divergence, where the momentum of the external legs to be 0. So this phenomena somehow saying that in a field theory on a non-commutative space, so UV or short distance physics and long distance IR physics are related to each other. So this non-local nature of the field theory on the non-commutative space gives some hint to the non-local nature of quantum gravity or quantum geometry, because some model of quantum gravity or string theory are given by the matrix model. Okay? So it's interesting to look at this kind of structure in the matrix models or some field theory on non-commutative space. Okay? So in this example, the relation appear the divergent structure. Okay? So let's try to look at this kind of relation in a direct way. Okay? Some physical quantity to look at this kind of a correlation would be the entanglement entropy. So entanglement entropy, inductively speaking, we divide Hilbert space into two parts, and you trace out one part and you calculate this kind of Von-Neumann entropy, and it measures how strongly correlated these two degrees freedom are. Okay? Often, this kind of entropy is considered for the position space, but of course, we can consider the entanglement entropy in momentum space. Namely, we divide Hilbert space into two parts, okay? Low energy part and high energy part, and look at the correlation. Okay? This would be the direct relation between the correlation for the high momentum mode and low momentum modes. So there is some well-established recipe to calculate this entanglement entropy. So the strategy is simple. So we start with some pure state, and to calculate entanglement entropy, we divide. I divide the momentum field into two parts, some lower part and higher part. And then instead of directly calculating this Von-Neumann entropy, okay, I first calculate the power of reduced density matrix rho L, which corresponds to calculate the usual the path integral calculation for with a special boundary conditions. For the low energy modes, we have just one relative boundary condition. But high energy mode, we prepare some bunch of copies. Okay, and just consider the path integral in this special boundary condition. I can calculate this reduced density matrix rho to the alpha, and we take the limit, then it reduces to the entanglement entropy. Okay, so this is a well-paved way. So I just walk through this direction. Now, this is short talk, so I just introduce some of the results. Okay, first, let me start with some tree-level calculation. Okay, so the actual formula is longer. It involves many of the cosine hyperbolic, sine hyperbolic, and something. Okay, sorry. But and here, this vertical direction corresponds to the time direction. I put some periodic boundary condition here. So this periodicity basically corresponds to the temperature. Okay. So the entanglement entropy I want to calculate corresponds to the zero temperature limit, which corresponds to the beta goes to infinity. Okay. So for the tree level, I can calculate some entanglement entropy. So in this zero temperature limit, it behaves like this exponential minus. Okay. So it's exponentially suppressed and goes to zero. This is actually what we anticipated because in Hamiltonian, the kinetic term is diagonal in momentum basis. So there is no entanglement here. Now we move on to the one-loop calculation. One-loop calculation, the Feynman diagram is like this. So this is one 4-point vertices and then contracting. So the red line corresponds to the high energy mode propagating, and the blue line corresponds to the low energy mode propagating. Okay, that's doing this calculation. And again, the actual the result is much more complicated. That I just show the limit with this the temperature limit theta goes to infinity. Again, this is exponentially suppressed. So there appears no contribution at this order. So we need to calculate a Turp calculation. So Turp calculation is I just prepare two vertices and contract it to various ways. And this is final result. Okay, it's not vanishing anymore. And one observation is that okay, here we prepare two vertices. They are contracted by various propagators. This red one is a high energy propagator, blue one is low energy propagators. As a result, I have observed that. Okay, so there appear three types of contribution, and this LLH means that one vertex has one high energy leg and three low energy legs. Okay? So there appears no contribution from all H, so something like this, or all low contribution. Okay? So somehow the graphs that involves both low energy mode and high energy mode contribute to this entanglement entropy. Here this omega is basically energy. So omega square is L plus 1 divided by R square. This is P square in the field theory, and this mu is mass. So this is basically momentum plus mass energy. And this Z term corresponds to the matrix structure, the algebraic part. Okay? So this part has a bit complicated structure. There appear three parts. It is planar, and there's two different types of the contraction, non-planar contraction. Okay. So let me look at some effect of the non-constitutivity. So there will be several ways. So one simple way is that if we consider the usual commuting field theory, there's no distinction between planar and non-planar diagrams, because the order of the field are not so important. So the one simple way is that just consider the difference between these three contributions, and all contributions are just regarded as just planar. Just neglect non-constitutivity at this algebraic in the algebra point. So this is some detailed calculation, and this is very complicated formula. Okay? So I just rely on the computer to calculate for some small n case how difference appears. So this is my result. So this is a result of the original one, and just force all terms to be planar. So there appear some difference. So actually, introducing the non-compatibility actually changes the value of the entanglement entropy. So far, this is a good result. And this work has not yet completed. Okay, one thing that's okay. So I have calculated a tool calculation I have done the tool calculation to calculate the entanglement entropy. Or this part. Okay. So later we have noticed that okay, this is the lambda squared contribution. There should appear a logarithm of the coupling constant lambda contribution, which would be the leading order contribution in the perturbative limit. So now we need to calculate this leading order part, and then complete the calculation. And also, finally, we want to compare our result with the usual field theory. Okay? In that case, this is a numerical calculation for somehow smaller size of the matrices. So it's more interesting to look at the larger asymptotic behavior of this algebraic part. So we need to establish some calculation, some tool for calculation of this kind of part. So basically, this is my thank you.
Okay, any questions or comments? If not, then let's thank the speaker again. And